All right, so the goal of today is to start talking about what is known as the normal force. The normal force, which is basically a force that is perpendicular to surfaces of contact, and we're going to elaborate more on that today. Before we get to that, I want to briefly review what we talked about last week. So last week we introduced Newton's three laws. Newton's three laws of motion. The first law that says an object at rest tends to stay at rest unless acted upon by an unbalanced force, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. Okay, that's Newton's first law. Remember, we call that the law of inertia. Inertia just basically means an object's resistance to change. All objects have a natural resistance to change unless some sort of force alters their state of motion or their state of rest, however you want to put it. So that's Newton's first law. Newton's second law basically is his mathematical law, and we've already talked about that, is force equals mass times acceleration. So it's Newton's mathematical law. Basically what that law says is that forces cause any object or any mass to accelerate. And of course, the acceleration is directly proportional to the force and inversely proportional to the object's mass, which we're going to talk more about that in the coming weeks. Newton's third law, we know that for every action, there's an equal and opposite reaction. So that law basically says if I push on an object, that object also pushes back on me. It's Newton's third law. Okay. Now, let me go ahead and share my screen briefly, because there's something that I want to go over that we talked about last week that will be important for our topic on today. And if you guys remember, last week we used Newton's second law, force equals mass times acceleration, to work out these various problems here. I want to regurgitate your memory of number 4, because we're going to be talking a little bit about weight today, and whenever we do these problems involve our normal force. So let me get my pen here. Oh, guys, give me just a second. Let me open this up in another program just to be sure I can write on it. Okay, so number 4 here says, it asks us, what is the weight of a 0.1 kilogram apple? Guys, remember what I said last week. If you stand on a scale, and as you're standing on a scale, you want to know your weight while you're standing on the scale. What is the scale measuring? At least what is it measuring indirectly? Let me say that. Well, indirectly, the scale is measuring your basically the scale is measuring the magnitude of the gravitational force pulling you down, right? Because there's a force of gravity that's pulling you toward the earth, and obviously the force of gravity is responsible for pushing you toward the scale. It's pressing up against you. Well, it's causing you to press up against the scale. That's what gravity is doing. So with that said, since the scale is basically measuring gravity indirectly, we would say that, let me write this here. We would say that the force of gravity is equal to an object's weight. Okay, the force of gravity is equal to an object's weight. Now, if y'all remember last week, I told you guys that I gave you guys this equation that the force of gravity is equal to an object's mass multiplied by the acceleration of gravity itself. So, what is the acceleration of gravity? Does anybody remember that number that I told you guys remember last week? Anybody remember the magnitude of the acceleration of gravity here on Earth?
9.98.
9.8. You're close. Thank you. Yeah, 9.8. So force of gravity is mass times 9.8. So if we have an apple, that has a mass of 0.1 kilograms, basically we need to plug in 0.1 into this equation and multiply by 9.8. And of course, that will tell us the force of gravity pulling down on the apple, which is 0.1 times 9.8 is 0.98 newtons. Okay. So what this tells us is that the weight of the apple is equal to 0.98 newtons. Okay. Because remember that, guys, anytime you step on a scale, basically the scale is measuring the force of gravity indirectly. So in other words, weight equals to the force of gravity pulling on you, if that logic makes sense. Okay. Could someone put the link in the attendance box for Leah? Okay, but the main thing that I want you guys to know here, because again, we're going to be using this equation a lot today, that the force of gravity is equal to mass times 9.8. Okay. And of course, whenever we work out our problems for the day, and also for the problems on the Schoology assignment, we're just going to go ahead and round 9.8 off to 10, just to make our calculations super easy. Okay. All right, so I'm going to stop sharing my screen there. Okay. Now, let us get into the main topic for today, and that is normal force. Okay, let me... In just a moment, I'm going to pull up this YouTube video.
Now we
Okay, so let's talk about the normal force. Okay, this is the first force, no, actually the second force that we're going to talk about in this class. Next class period, we're going to go into more details with other types of forces. We've already talked about the force of gravity. That's a force you guys are familiar with. Today, we're going to talk about the normal force. And basically, what the normal force is, the normal force is basically a contact force. It arises from two objects in direct contact with each other. And the normal force is always perpendicular to the surface of contact. So what is it that I mean by that? Okay, well, let me give you guys an example. Okay. So imagine that I'm holding up here two books. So I have a white book, and I have a book in blue. Okay. As you guys can see, the blue book is sitting on top of the white book. Okay. Now, guys, the question is right now, if I solely had to look at the blue book, this blue book right here, how many forces right now are acting on the blue book? Okay. Well, it turns out there are two forces acting on the blue book. For sure, I know that there's gravity acting on the blue book, right? So there's a force of gravity pulling downward on the blue book. But guys, notice, do you see the blue book accelerating downward right now, toward the center of the earth? Or is it going through the white book? No, it's not going through the white book. So that means if there's a downward force pulling the blue book down, there has to be another force balancing the blue book, and that force is acting upward. Guys, that force is what we call the normal force. That's the name of the force in this case. It's the normal force. Why is it called a normal force? Well, notice the blue book is in contact with the white book. Okay, so the blue book is in contact with the white book, and we know gravity is pulling down on the blue book. But in order for the blue book to just be sitting still, in order for it to be at rest, forces have to be balanced. So that means the white book itself, the surface of the white book is pushing upward on the blue book. Okay, so because the blue book is in direct contact with the white book, there's a normal force that arises from that surface of contact. And of course, we always said that the normal force is perpendicular to the surface of contact. And we know that, right? Because this right here, this is the surface of contact here. So the normal force points straight up. It's perpendicular to that surface. Okay. I'm going to put on this short 3-minute YouTube video that I think does a good job of really explaining what I just said.
Now we can consider the normal force. So our first question.
Let me make this louder so you guys can hear it better.
Now we can consider the normal force. So our first question is, what do we mean by normal force? Let's start with one word at a time. Force, we've already talked about, is a push or pull on an object. So then we get to normal. Now what we don't mean by this is it's not an ordinary force. While they happen all the time, that's not the usage of the word normal we mean. Instead, we're talking about a mathematical definition of normal that refers to the perpendicular. So for example, if I have a surface, my normal force is always going to be at a 90-degree angle perpendicular straight out from that surface. And I use the F with a sub n as my symbol for it, both capital F and capital N. So here's some examples. Again, if I have a horizontal surface, my normal force might be straight up from that surface. If I have a vertical surface, my perpendicular is going to be, say, out to the left. And if I have a sloped surface, my normal force is still going to be perpendicular, but that means it's going to be off at an angle. Now, when do you have the normal force? Anytime you have solid surfaces in contact with each other. The normal force is the force that prevents those solid objects from going through each other. Now, from Newton's third law, we know that forces come in pairs. So let's understand that in terms of a normal force. The ground pushes up on the block with a normal force, but the block also pushes down on the ground. If I push on the wall to the right, the wall pushes back on me to the left. These are force pairs. I push on it, it pushes back on me. In both cases, I can't push through the wall and the wall doesn't push through me. Now, if I've got multiple surfaces, like I have in this example, I have to consider a normal force for each one of the points of contact. So for example, up here at my hands, I have a normal force where I'm pushing on the wall and the wall is pushing back on my hands. In this case, my front foot is going to have a second normal force, where my foot pushes down on the floor and the floor pushes up on that front foot. And in the back foot, we have a third normal force. And again, it's a force pair where my foot pushes down on the floor and the floor pushes back up on my foot. If I have multiple objects, I need to consider the surfaces for each one of those objects. So here I've got two boxes sitting on top of each other, sitting on the floor. Well, there's a surface between the two boxes, and so the green box pushes up on the blue box, but the blue box is also pushing down on the green box. And there's a surface contact between the green box and the floor, so that the floor pushes up on the green box and the green box pushes down on the floor. When I go to do force diagrams, remember that I want to treat each object separately. So my blue box has a normal force upwards due to the green box, and my green box has two normal forces, one due to the floor and one due to the box sitting on top of it. Now don't forget, both of those boxes also have a force of gravity, assuming they're sitting here on Earth and not out in space. And so your full force diagram would have to take into account not just the normal forces, but any other forces that are on there as well. So that's your introduction to the normal force.
Okay, and I will put that video in YouTube. Well, I'm sorry, I will put the YouTube link in Schoology, so that you guys can go back and rewatch that, in case you guys want to look over those concepts again whenever you guys are working on the assignment later on today. Okay, so now basically the rest of the time today, I just want to just be going through several examples that are going to look like some of the examples you are going to see on your assignment for later on today, or whenever I end class. Whenever I end lecture. I'm going to end lecture, but I'm going to keep the Zoom class going, so that just in case anybody has any questions for me, they can come back to the Zoom call and ask. Okay, give me just a second while I pull up this file for you all. But remember what she said in the video, guys. Anytime you have two objects in contact, you're going to see a normal force there. So that will help you with understanding the, conceptually, how to know where a normal force appears on your diagram. You guys, give me just a second. I'm trying to get the right file open. Okay, this I had a PowerPoint, but in order for me to use it in Common, it has to convert over into a PDF, and so that's what's going on now. So it's converting. As soon as it converts, I'm going to share my screen. Okay. Again, I want to work out some examples that are going to look like some of the examples that you guys are going to see later on, whenever you guys are working on your assignment. Okay, now before we get into a few mathematical problems, okay, let me write down the equation for the force of gravity, because that equation, you guys will need to know that equation for this assignment. Now, okay, so last week and also at the beginning of this class period, I told you guys that the force of gravity So if you want to know the magnitude of the force of gravity, it's always equal to an object's mass times 9.8. Okay. Now, in order to make these calculations simple, I'm just going to round 9.8 out to 10. Um, so mass times 10 will be our equation for the force of gravity. Now again, and the actual value is 9.8, but for the sake of simplistic problems, we can round 9.8 off to 10. Okay. So now with that said, okay, guys, look at what I have here on the screen. Okay, so I have a blue box here, and this blue box is sitting on this table. Okay, so as the blue box is sitting on the table, obviously there's two forces acting on it. Oh, by the way, guys, I forgot to write this down. Uh, let us assume this blue box here has a mass of 3 kilograms. So that this box has a mass of 3 kilograms. Okay. So 3 kilograms is the mass of the block. Okay. So now, so there are two forces acting on my block. Okay. We already know that there's a force of gravity pulling down on the block. So I'm going to draw I'm going to draw an arrow to represent gravity. Okay. So there's gravity there. Gravity is literally pulling the block down. Okay. But obviously, guys, you don't see the block going directly through the center of the table. Okay. So in fact, what you see is that the block is just sitting there. So there means there has to be another force balancing this force right here. Well, what is that force? Well, we just said it's the normal force. Notice the block is in contact with the table. So the surface of the table is literally pushing up on the block. So I'm going to draw another arrow to represent that. And I'm going to try my best to make these forces, these arrows, roughly around the same size. So the surface of the table is pushing up on the block, and that is the normal force. Can someone tell me the magnitude of the normal force? Does anyone know? Can any can anybody look at the diagram and tell me how many newtons is the value of that normal force? Well, first of all, someone tell me what is the magnitude of the force of gravity acting on the block? Anyone know? Well, we know the block has a mass of 3 kilograms. So, guys, what is 3 times 10? 3 times, I'm sorry?
Yes.
So, what is the magnitude of the force of gravity here? So, 3 times 10 is 30 newtons, guys. Okay. So, that means the force of gravity pulling down on the block is 30 newtons. Now, since the block is at rest, these two forces must be balanced. So that means if gravity is 30 newtons, then that immediately tells us that the magnitude of the normal force is also 30 newtons. Okay. Everybody got that? Okay, so that's an easy one. Again, let's do a few more. Again, we're gonna start off working easy ones, and then we're gonna gradually get to ones that are a little bit more complicated. So let us look at this one right here, this situation right here. So, okay, let us assume this block here is 7 kilograms. Okay. If this block here has a mass of 7 kilograms, let me just draw it on the block. So this block here has a mass of 7 kilograms. Okay, the question is, how many forces are acting on this block, and what are the magnitude of those forces? Okay, so we know for a fact that there's clearly gravity acting on the block. So let me draw the force of gravity. So clearly there's a gravitational force acting on the block. Okay. But there has to be another force to balance that because the block is not moving. So the surface of the table itself must be pushing up on the block. and that force is what we're going to call our normal force. The normal force is basically a force that is perpendicular to the surface of contact. So here's the surface of contact here between the block and the table. So the normal force is 90 degrees relative to that surface. So the normal force points straight up. So what are the magnitude of these forces? Well, remember what we just said, force of gravity is equal to mass times 10. So if the block is 7 kilograms, the magnitude of the force of gravity has to be what? Anyway, what's 7 times 10?
70.
Yep, 70 newtons. So that's the magnitude of the force of gravity right now pulling down on this block. But guys, remember there's another force also acting on the block, on the red block here, and that is the normal force. So that means this value here for this normal force has to also be 70 newtons. And again, the way we know that it has to be normal force, that the normal force has to be 70 newtons is because this block isn't going anywhere, both the forces that are acting on it, the up force and the down force, have to be balanced. So if one force is 70 newtons, then you know that the other force is 70 newtons. Okay. Let me get into another example. This one is a little bit more complicated. Let us suppose I have a blue box here sitting on a table. Okay. And this blue box here is 5 kilograms. Okay. Now, let us imagine that while the blue box is sitting on the table, let us imagine that someone comes along and they decide to push down on the blue box. Let us say that they push down on the blue box with a force. Let me draw an arrow here. What if they push down on the blue box with a force that is 60 newtons? Okay, so this force that I drew in black is 60 newtons. Okay. So I want you guys to imagine what's happening here. It's kind of like this. Imagine, just kind of imagine what I'm saying here. So, for instance, like imagine that I have, a blue book sitting on some surface, and imagine that while sitting on the surface, I'm pushing down on the surface, like I'm pushing down really hard on the surface. Now, as I'm pushing down on the surface, guys, if you notice, the blue book isn't going anywhere, even though I'm pushing down on it. So, guys, let me ask you a question. As I push down on the surface, what do you guys think happens with the normal force here between this white book and this blue book here if I push down on it? Do you guys think the normal force increases or decreases? What do y'all think? Well, I'm telling you guys right now, the normal force would have to increase, right? Let me show you guys why. So as I'm pushing down on a book, okay, here, there are other forces involved here. Well, this book or this block, whatever you want to call it, this blue box. As I'm pushing down on this blue object, let's say I push down. Oh, I just realized. Was I supposed to write that? Yeah. Hold on. Yeah. Okay, so there's more than one force involved here. Okay, so so we know there's gravity. There's gravity pushing down on the block. Okay. And also there's a normal force. Basically, there's a normal force also acting on this block here. And so the normal force is caused from the surface here, the surface of this table pushing up on the block. So the question is, what is the magnitude of both these forces? Well, I immediately know the magnitude of the force of gravity. And I know that because the force of gravity is always equal to the object's mass times 10. So 5 times 10 gives me a magnitude of 50 newtons. Okay. Okay. Now, guys, here's the tricky part here. What is the magnitude of this normal force here? How large is this normal force pushing up on this surface? Anybody got an idea? I'm gonna tell you guys right now, if the block is not moving, all of your up forces should balance all of your down forces. Anyone want to tell me the magnitude of this normal force here? If I have two down forces here, I have someone pushing down on the block, and I also have gravity. I also have gravity pulling on the block. What has to be the value of the normal force here in order for the block to still be at rest? Anyway, remember, your up force has to balance your two down forces. Well, our two down forces is, we have one force that is 60 newtons, and we have one force that is 50 newtons. So 60 plus 50 gives us 110. So that means the magnitude of my normal force is 110 newtons. Okay? Make sense? Let's do another example. Again, the more we do, the better. Okay, so let us suppose in this example right here, let us suppose I have an 8-kilogram box. And again, your problems on your homework will be just like this. Let us suppose I have an 8-kilogram box. So 8-kilogram box. And let us suppose that I'm pushing down on the box. So I'm going to draw a downward force. So imagine that I'm pushing down on the block here. And let's say the magnitude of the force that I'm pushing down on this block here is 20 newtons. So I'm pushing down with a 20 newton force, and it's an 8-kilogram block. So the question is, what is the magnitude of the other forces involved on this block here? So obviously we know there's other forces involved. We know, in addition to someone pushing down on the block, there's obviously gravity pulling the block down. But notice it's in contact with the surface of the table. That means the table itself must be pushing up on the block. So remember, the equation for the force of gravity is equal to mass times 10. Okay. So that means if I want to know the magnitude of the force of gravity acting on this block here, so let's say there's gravity pulling down on the block, and so force of gravity is always equal to the object's mass times 10. So this mass of this block here, this red block, is 8 kilograms. 8 times 10 is obviously 80 newtons. Okay. Now, with that said, can someone tell me, if I know these two down forces acting on the block, what is the magnitude of the normal force pushing up on the block? Assuming the block is at rest. Okay. So remember, guys, if the block is at rest, remember, all the forces must be balanced. So it's not accelerating anywhere, so all the forces must be balanced. So remember, guys, if the forces are balanced, our down forces must balance our up forces. So in other words, the one up force we have here must balance the two must balance the two down forces. So if I'm pushing down on the block with 20 newtons and gravity is pulling on the block with 80 newtons, can anyone tell me the magnitude of the normal force, which represents the surface of the table pushing up on the block? Anyone? Come on, guys. Y'all have to know how to do this. This is what you're going to be doing for your homework for tonight. Or, whenever we get done with the Zoom call. Some of you guys want to get done now. So what is the magnitude of this normal force here? Well, since this force is 20 newtons and this force is 80 newtons, 20 plus 80 is equal to 100. So in this case, the magnitude of my normal force is 100 newtons. Okay. Before I work out about two more problems, and then I'm gonna let you guys go, I want to show you guys something here. So that whenever you guys are working on the assignment for today, you guys want to be confident about what to do. So, one of the things that the assignment is going to ask you all later on today is that it's going to ask you guys, are the normal forces labeled correctly? So, for example, uh, look at situation A here. It says Jim is leaning against the wall with 1 foot. Draw and label all the normal forces acting on Slim Jim. So, guys, if we want to know the forces acting on Jim, okay, so what are all the normal forces acting on Jim right now? Well, in order to know this, guys, basically you guys want to look at, the surfaces of contact. Okay, so there's two surfaces of contact here. Notice Jim is in contact with the floor, and he's also in contact with the wall. So that means there must be two normal forces acting on Jim. And guys, in what direction do they act? Well, think logically here, guys. If Jim's foot is pushing down on the floor, that means the floor itself must be pushing upward on Jim, right? And it must be pushing upward because, again, we're concerned with the forces acting on Jim, not the forces acting on the floor. So that means here's a normal force acting on Jim, and it's pointing straight up. And then there's also a normal force acting on Jim, and it's pointed in this direction right here because the wall is pushing on Jim. Okay, I don't know if you guys can see that arrow. Okay. And how do I know it's pointing that direction? Well, guys, think about it. It's Newton's third law. Remember, if Jim pushes on the wall pushes back on Jim, and we're concerned with the forces acting on Jim. So, what are all the forces acting on Jim? That's the key. That's the key word here. Okay. What about this situation right here? Okay. If Jim is standing on a surface, if Jim is standing on a surface here, and both of his feet are on the ground, how many normal forces are acting on Jim here? Well, there's 3 normal forces acting on Jim because there's 3 surfaces of contact. There's a surface of contact here. So there's a normal force acting upward there. Okay. There's also a surface of contact here, so that means there's a normal force acting here. And then there's also a surface of contact here, because Jim is in contact with the wall, so that means there's a normal force acting like this. Okay. All right, so that makes sense. That makes sense why the normal force is pointed up here, because Jim's foot pushes down on the ground. That means the ground must be pushing back upward on Jim, according to Newton's third law. Okay, let's look at another example here. So Jim is standing on a table and pushing on the ceiling. How many normal forces do we have here? Because remember, the instructions said to draw all the normal forces acting on Jim. So actually here, we actually have 4 normal forces. We have 4 normal forces because we have 4 surfaces of contact. Okay. So notice how his feet is in contact with the table. So that means the table must be pushing up on Jim like this. So that's a normal force there. Here's also another normal force because, that's another surface of contact. Okay. So, and again, those arrows are pointed straight up. Okay. Now, guys, let me ask you a question here. What about the normal forces acting on Jim here? Notice how Jim is pushing on the ceiling. So, what are all the normal forces acting on Jim here? Because he's in contact with the ceiling. He's touching the ceiling. The normal force is a contact force. Well, guys, what does the arrows point here? Hopefully this should be obvious. It should be obvious because if Jim is pushing up on the ceiling, according to his third law, the ceiling must be pushing down on him. So if we're concerned with the forces acting on Jim, that means there's a normal force acting like this on Jim. And there's also a normal force acting right here on Jim, because the normal force represents all of the surfaces of contact. Okay, everybody got that? Okay. You know what? Before I look at number 2, I want to look at number 3. Not number 3, but I want to look at this diagram here. So if we have a roller coaster here, how can we label the magnitude of the normal force acting on the roller coaster? So, well, how can we label the direction of the normal force acting on the roller coaster? So look, there's a surface of contact here, so that means the normal force must be pointing in that direction, because the normal force is always perpendicular to the surface of contact. Okay. What about here? Okay, so here this surface is, looks like this, so the normal force is pointing straight up here. Okay. And what about here? Where does the normal force points here? Here the normal force is also points straight up. Okay. Here, because the surface is at an angle, the normal force points in this direction. But here, the normal force points straight up. When we look at these surfaces here. Okay. Okay. Guys, look at number 2 here. I briefly want to label a few things here. Number 2 says, if a surface has to support more, it has to provide more normal force. Does the following increase or decrease the normal force? Okay. We've already said what happens here. If you push down on an object, that increases the normal force acting on that object from the surface beneath it. So for here, I'm going to put I for increase. So pushing down on a surface increases the normal force. What if you set another object on top of that object? Well, that should be obvious. Setting another object on top of that object is similar to pushing down harder on it, so that also increases the normal force. Okay. What about the frictional force? So, guys, if I have let's say I have two objects here, and one slides across the other. So as it slides across the other, there's clearly friction uh, between the two surfaces. But guys, friction in this case will be a horizontal force, not a vertical force. So friction does nothing to the normal force. So I'm going to put an N here for nothing. Okay, friction does nothing to the normal force. Um, what if you decrease the weight of the object? So guys, imagine you had an object sitting on a scale, and the scale pushes back on the object. If you decrease the weight of the object, let's think logically here. What's going to happen to the value of the normal force? Well, that should be obvious. Decreasing the weight of the object should decrease the magnitude of the normal force. And that should be obvious because by decreasing the weight of the object, there is less, basically there's less gravity pulling down. Now, what about this situation right here? This is a situation we haven't talked about here. What happens when you pull up on an object? So we already talked about pushing down on an object. So if I have this book here, we know that pushing down on the blue book increases the normal force here. But what if I slightly pull up on the blue book? By me slightly pulling up on the blue book, that should be the opposite. That should decrease the normal force. Okay. So pushing down on an object increases the normal force. Pulling up must decrease the normal force. Okay. What about increasing the weight of an object? Increasing the weight of the object must increase the normal force because you have more gravity pulling down on the object. What about pushing sideways on an object? So pushing sideways, that's a horizontal force. So in this case, it's not going to affect the vertical forces. So pushing sideways on an object does nothing to normal force. Pushing down at an angle, you're still pushing down, so that should increase the normal force. Okay. I tell you what. Do I want to do one more example? You know what? I'm gonna do one more example here, and I'm gonna let you guys go. Okay. One more example. Okay. Guys, look at situation C here. So I have a 4-kilogram block sitting on a table, and while this 4-kilogram block is sitting on a table, there's clearly an up force. So someone is pulling up on the block with a 20 Newton force. Okay. Now, okay. So, let us label the remainder of the forces acting on the block and list the magnitude of those forces. So, we already know that there's clearly a force of gravity pulling down on the block. Okay, so there's a force of gravity pulling downward on the block. Okay. What is the magnitude of the force of gravity here? Remember, force of gravity, we're going to use the equation mass times 10. So the block is 4 kilograms. That means the mass, if the mass is 4 kilograms, that means the force of gravity here is 4 times 10, which is 40 newtons. So 40 newtons represents the magnitude for the force of gravity. Let me do that in green. Now, there's another force acting on this block here, and that force is the normal force. Okay, so guys, the question is, what is the magnitude of this up force right here? What is the magnitude of this up force? I want you guys to think about it. If this block is at rest, basically that means whatever this down force is, these two up forces have to balance it. Right? So what is the magnitude of this normal force that I drew? what does the normal force equal here? So Fn stands for normal force. All right, guys, it's the last one. So come on, guys. Someone answer me. What do you guys think is the magnitude of this normal force here? It's not 60. It would be if the Pablo, if you were pushing down on the block, then it would be 60. However, you're not pushing down on the block. Notice, someone's pulling up on the block. So that means this force plus this force has to equal this force, right? Because your down arrows have to equal, your up arrows have to equal your down arrow. You're right, it's 20. You guys got it. So everybody got that? Both of your, in this case, all of your up arrows have to equal your down arrow because the forces have to be balanced. I'm going to say that again. In this case, the up forces have to equal to the down forces. So that means since we have two up forces here, both these forces combined must be equal to this one down force because the object is at rest. So that means you guys got it right. It is the normal force has a magnitude of 20 newtons. Okay, because 20 plus 20 is equal to 40. Okay. That's pretty much all I have for the day. In just a moment, give me about 10 minutes while I get the normal force assignment uploaded into Schoology. It is all multiple choice, but you guys have to be sure you understand everything we did today in order to be able to do it. So again, guys, give me about 10 minutes, 5 to 10 minutes, and I'll have that assignment uploaded into Schoology. Are there any final questions before me? Guys, if there are no more final questions for me, you guys are free to go. Or if you want, you can just hang around and do the assignment while I'm on the Zoom call because I'm gonna keep the Zoom call open up until 9:11. I'm gonna keep it open because that's when class ends. So, but you guys are free to go if you guys want to. Other than that, if there are no questions, you guys can. Again, you can either hang around here or you can sign out. It's totally up to you. Have a good one, guys. Bye.